All right, welcome back. So we'll begin our session 2 for the invited speakers. So we're very fortunate to have Roya Firoozi here with us from Stanford. She's a postdoctoral fellow with Max Schwager in the Aero and Astro department and works on in the multi-robot systems laboratory. And her research interests are at the intersection of control theory, optimization, and machine learning, exactly what we all like here. So, and her interests are in building, efficient and safe decision-making and planning algorithms, to look at and fault diagnostic techniques within autonomous agents, but in these specific complex environments, which she'll talk to us about in terms of the interactive autonomy in different types of complex environments. So welcome, Roya. We can get started.
Thanks for the kind introduction. Today, I'm going to talk about interactive autonomy in complex environments. We can categorize interactive planning into predict, then plan, or NPC-like approaches, or predict and plan, or game theoretic approach. In predict, then plan, prediction and planning are decoupled. We first predict the plan of other agents, the intention of other agents, and we freeze their trajectory and incorporate it into optimization. In game theory, we consider instead mutual influence and plan based on with the hope that if needed, the other agent is gonna slow down or speed up to resolve the conflict. So in MPC, the optimization is solved for only Z, which is a state of ego agent, but in game theory, the optimization is solved in joint state of all the agents, is capital Z here. And in both cases, we need to know what is the intention of other agents and to be able to do prediction. In today's talk, I first focus on predict, then plan, or distributed MPC. Then I talk about predict and plan, in which the prediction and planning are coupled, as opposed to MPC that prediction and planning are decoupled. And at the end, I focus on a mutual influence between interactive agents and how we can quantify the interaction in dynamic games. We can formalize a coordination task between multiple agents as a single optimization problem. We have m number of robots with different constraints. The collision avoidance constraint is coupled between the robots. We can simply model the robots as circles and find their distance as center to center of these circles. But this way is overly conservative modeling for collision avoidance. And for a tight maneuver like this, when multiple autonomous vehicles are merging into the same lane, if we model the robots as a circular shape, we cannot solve such a tight maneuvering problem. So to allow navigation in tight environment, we can model the robots as arbitrary polytopic shapes. And the distance between the two polytope, like polytope 1 is robot 1, polytope 2 is robot 2, and the distance between the two is defined as the optimization in which we minimize the Euclidean distance subject to definition of the polytopes here. And we want this distance to be greater than or equal to d mean, which is a design parameter that we choose as the safe distance between the two polytopes. But here, this collision avoidance is a constraint of a coordination problem. So we have an optimization as a constraint of another larger optimization. We end up with a bi-level optimization, which can be computationally intractable for large number of agents. So the idea is how to remove the need for solving a bi-level optimization and come up with a single optimization formulation for coordination paths. We can use a strong duality in which this primal formulation for finding the minimum distance between the polytopes is equivalent to the dual problem, in which we introduce the dual variables which are coupled between the two polytopes, lambda 1, 2 and lambda 2, 1, and we want to maximize the objective in dual, which is equivalent to Euclidean distance between the two polytopes. But since we want this, and it is still an optimization, it is still a maximization, and to be able to remove the need for solving an optimization, we said that we want this distance to be greater than or equal to the mean. So instead of solving a maximization, we can just solve a feasibility problem. So we can impose all the constraints in the right as the constraints of the optimization. So instead of solving a bi-level problem, now we can just solve the coordination as a single optimization by imposing the feasibility constraints of collision avoidance. And here, it's a simulation of robots with arbitrary polytopic shape. They can do tight collision avoidance, like in the center of the circle, they always maintain the minimum distance that we have predefined. And the problem is solved using MPC. The dots in front of the polytopes, and they are open loop trajectories, which are the solution of MPC planner. Here it is still a centralized problem, which can be computationally expensive, and it's not scalable with respect to the number of robots. So the idea here is how to devise this, how to devise a distributed algorithm in which we split this large optimization into a smaller subproblem that each robot can solve independently. And is suitable for online applications, for it has an efficient computation time. We can use the communication between the robots, and they can communicate their open loop trajectories, which are solution of MPC. So we use this communication, and at the same time, we can exploit the dual structure of the problem. And since we have introduced dual variables, now we can use them for splitting the problem into smaller subproblem in an ADMM-like algorithm, in which we alternate between the primal variables and dual variables to be able to decouple the problem into smaller subproblems. So in the blue part, we're solving the NMPC problem for primal variables, which are Z variables, a state of the robot. And in the red part is the collision avoidance part, in which we're solving for dual problems, which are responsible for dual variables, which are representation of collision avoidance and coupling between the agents. So each agent independently can solve NMPC by fixing the dual variables. So bar notation here means that we fix the dual variables and we solve for primal variables, like we solve the state for the state of the robot, which is Z. And in collision avoidance, we keep all the primal variables as fixed and solve for dual variables. And then we alternate between these two, and each robot does this alternation separately. So we come up with a fully distributed algorithm, and for the same merging scenario for 3 vehicles that I just showed you, centralized approach is not suitable for online application, but distributed one. We have we have NMPC and collision avoidance. Collision avoidance is a simple QP. We can solve it in milliseconds. Nonlinear MPC also is suitable for online applications. And if we write the KKT conditions for the primal problem, we can end up with interesting geometric representations for these dual variables. Here we can visualize this result. In this picture, the left side, we have polytope 1 and polytope 2, and the green lines are separating hyperplanes that supporting hyperplanes that support each polytope at the X star and Y star. And their affine terms, they are actually the difference between the affine terms are the term that we have in the dual formulation for the distance between the two polytopes. And the maximization of this separation is equivalent to minimization of the primal problem. So, and it is true for any convex, any arbitrary convex shape, that if, for example, here, this blue part is a representation of Euclidean distance from primal problem, and this is not optimal here, so the separation between the supporting hyperplane is not maximized. In the last figure, the Euclidean distance is minimized, so the blue line is the smallest one, and the separation between the green lines is maximized. And if we visualize these hyperplanes, we can see how they're evolving as the vehicles are merging to the same lane. And this primal dual algorithm is computationally efficient, and especially for tight environment, it is suitable for tight maneuvering. Next, I'll focus on predict and planning approach, or game theoretic planning. So the same question also, what is here, that what is the intention of other agents, how we can predict their behavior. And the common approaches in game theory, they assume that we have a knowledge about the objective or intention of other agents. But in reality, we don't know what the other agent is gonna do. So the idea here is to use a communication between the agent and share the intention or objective between them. But we're not going to rely on the communication that we receive as the cost function of other agents, because communication might be faulty. And the idea here is to use a Bayesian filtering to evaluate the reliability of communication. For that, we assume that we have access to a number of hypotheses for intention of other agents. The cost is a combination of what the agent has communicated to us, the communicated cost, and different other costs based on each hypothesis that we might have for other agents. So to come up with a measurement for our filtering, we need to compare what has been communicated to us and what has been, the agent is actually executed, what we have observed. But to come up with, to be able to compare these trajectories, we need to solve the game for all different hypotheses that we have and find all the open loop Nash solutions for different hypotheses. Then we can compare those open loop trajectories with the executed trajectory to see how reliable is the communication. And then in game theoretic planning, we communicate all the costs, we receive the costs from other agents, we solve dynamic game, and after receiving the cost, we need to also, based on our belief about different hypotheses, form our own costs about the other agents' behavior, solve the game, execute it, observe the state of others, update our belief about the likelihood of what hypothesis is going to happen, and repeat in a receding horizon fashion. And here, if we compare the the two approaches, game theory with Bayesian filtering and the one without Bayesian filtering. The left one is the one that doesn't use Bayesian filtering, and there is a collision between the blue and yellow cards, and in the right, there is no collision, because in the right, they're using adaptive cost for other agents. Like as they receive the communication, they also have their own hypotheses and form their own costs for the other agents' behavior. And here, the yellow one is actually the one that is sending faulty communication to the rest of the agents. So game theoretic motion planner leverages inter-agent communication and generates safe trajectories in the presence of faulty transmission. In the last part of the talk, I'll focus on mutual influence between the agents and how we can quantify the interaction in dynamic games. When we have a large number of agents in the scene, let's say we have 20 agents, we cannot solve a full game for this number of agents in real time. This type of problem is intractable. So we need to choose a neighbor set and solve a local problem instead of the full game. One naive approach is that, for example, in this picture, the agent number one might consider only the orange circle as its neighbors, and agent number two can consider only the pink one as the number of agents that it wants to consider as neighbors, and it wants to solve the game with. But this type of choosing neighbor is very naive, because what if a neighbor who is very close to you, they're moving in completely opposite direction? So how we can come up with a better principled way of selecting the players? So we studied a couple of approaches. The first one was nearest neighbor that I just talked about. We can also work with Jacobian and Hessian and see how the collision cost is for each agent is sensitive to the action of other agents. This is we have a proxy for this collision cost. Actually, here is defined to have to be inversely proportional to the collision avoidance constraint between the agents. So this the larger this score from Hessian and Jacobian is, the more interaction we can consider. We have another criteria, cost evolution, with, in which we also consider one step in the past. And if this value is negative, we know that the agent is moving far away from us, so we can easily ignore the agent. And we also have used barrier function and control barrier function to quantify the interaction between two pair of agents. For example, between agent I and agent J, we can define a barrier function, which here is h of I jx greater than or equal to 0. These are safety constraints that are used for guaranteeing safety. But here, if we be able to satisfy, here we use it as a measure, as a score for measuring the quantification, measuring the interaction between the agents. So the higher this score, it means that the agents are farther away from activating their collision avoidance constraint. So higher score for low for barrier function or contour barrier function means low interaction. And here is a summary of all these pairwise scoring between the agents and how it is related to the interaction between them. And here is the numerical result that we have for 9 number of agents. The blue one is the equal one. The red ones are the agents that we consider into the game. The green ones are the ones that we ignore. And if we compare nearest neighbor with CBF, from time 0 till like from left to right, we have a snapshot of time. And for example, looking at this one, the ego agent is moving down, but nearest neighbor considers this one as a neighbor. But here, CBF quickly realizes that this neighbor can be ignored because the neighbor is moving in a direction that is not on your way. So you can simply ignore that and instead consider this agent as the neighbor because it's moving towards us. And finally, there are some challenges that I'm interested in to solve is that like different agents, they have different characteristics, capabilities, and configuration. Also, there's high variability in the environment. How can we tackle with all these uncertainties and to enable robust and adaptable interactive strategies through offline learning and online fast adaptation while we guarantee safety during the adaptation phase? Yeah, with this, I acknowledge my collaborators and thank you for your attention, and I'll take the questions.
You have time for a question.
So in the first part, you used volumes. Is there any work on using kinematics? So there's more property of so much stuff. I think you assume that the robot can move in any way.
They have the cars, they have bicycle model. They are actual model of the cars, which is very standard for planning in industry. And polytopes, they are unicycle models. Yeah.
In the second part for the CBS, do you use that to enforce safety? And also, is the CBF like parameter robustness, is that fixed?
Yeah, it is fixed. You're not using that for safety. You're just using them like outside of the game to just, yeah, it is possible that one can be like, it can be an extension of this work to have CBF also included in the game. For now, it's just outside the game. Based on the CBF score, we decide which agents to consider, yeah, as a measuring function.
Thank you very much. Thank you.